Good. All right. So I want to present an application of PhunKex that is related to gravitational wave astrophysics, which is very close to my heart. And so black hole mergers are now no longer a curiosity. We can detect some of these events almost on a daily basis when, well, not on a daily basis, but many over a month when the LIGO detectors are operating and collecting data. And as you can see here, as these instruments continue to increase their sensitivity, we get to see more and more of these events. And so here you can see how in the last observing run, there was a massive increase in the number of events that these observatories can detect. This is all really good. This means that we are now beyond the era of first detections. We are now entering the astrophysics era where we can do a statistical analysis of these sources. And there is someone fiercely typing in the background. If you could mute, that would be great. Now, the challenge that I want to describe here is that when we talk about AI in the context of gravitational wave astrophysics, we want to talk about the really challenging problems, not prototypes that try to handle a low-dimensional parameter space, but something that the production scale pipelines that LIGO scientists have developed over the last 3 decades really compete with AI. And so the problem that we are considering here encompasses black holes that describe a 4-dimensional signal manifold, the masses, and the Z component of the spins. To sample this parameter space, we require about 1.5 million waveforms, and then we need to contaminate them with several realizations of real LIGO nodes. So this demands the use of supercomputing, and we have been using Summit to train these models. Using over 1,500 GPUs, we can train these models in about 1.2 hours. And we have also shown that we can use up to a fourth of the system with strong scaling. Once we have these models, then we came up with the idea of using an ensemble so that when we find an event, we have the opinion not only of just one model, but of several models. And when all of them agree, not taking averages, when all of them agree that there is a significant event, then we go and follow up that particular noise anomaly. And so with this approach, what we found is that we can process advanced LIGO data faster than real time, which is not a given because these models in principle are characterizing a high dimensional signal manifolds. And what we found is that with this new approach, we were able to reduce the number of misclassifications from 1 every 200 seconds with the first generation of models that we developed a few years ago to 0 over 1 month of data, which is pretty good. And here is the money plot. You see this is 1 month of data, and in green you see when the detectors, the 2 LIGO detectors are up and running, in gray when one of them is not collecting data. And so we blaze through this month of data using 64 GPUs in about 7 minutes, all right? So this is good, but not good enough, because when you present this type of results in a paper, people question whether this is for real, whether they can reproduce the results, where are your models? And so what we did was to leverage the Data Learning Hub for Science. We made the models open source, including the post-processing software needed to go and find these gravitational wave sources. We realized that DL Hub is great because you can access these models, you don't worry about libraries, but then there's still the question, can we do better than this? And the answer is yes. If we now combine models that are trained with supercomputers, you make them available through DL Hub, and then you still combine this with PhunKex to reproduce the analysis, then you're addressing multiple problems here. One is you provide an entire pipeline to reproduce the analysis. People can use whatever compute resource they have available, so long they deploy a PhunKex endpoint. And this also addresses sociological issues because you give them everything they need. Fully trained models, containerized, a way to distribute the analysis, and they can use whatever GPUs or cloud resources they have available. And so for the first set of results that I presented to you, those were obtained by my students. And here you see the results obtained by Argonne and Chicago scientists, completely independent to us. I think they are not experts handling gravitational wave data, but the code that they used was self-contained. So they were able to just follow the steps and reproduce our analysis, and the scalability was again pretty good. Results were the same. And so with this approach, we are addressing issues about scalability, reproducibility, even interpretability. So the combination of DLHub and PhoneCakes is great for this type of work. Now, this is the static approach that we are using at the moment. If you have access to a supercomputer, you can train the models, you make them open source. People leverage PhoneCakes, they can reproduce the analysis. If you go the extra mile and rewrite the models using TensorRT, you can even save more time. And there is no loss in accuracy in these models. What TensorRT does is it optimizes the models for inference and reduces the size of them. So they are ideal for inference at the edge. If you want to read about this work, you can go and read the Nature paper, or you can go and see the human aspect of what it meant to work with Kyle, Ryan, and all those great researchers at Argonne and UChicago. And you can see other blogs like this one from a developer perspective. What is the type of technology that we use to realize this work? And looking ahead in the future, we want to take this to the next level, but in a dynamic approach, so that you don't need to go all the time to supercomputers to train these models when the statistics of the noise of, for example, LIGO or any other facility changes over time. We want to create other loops so that you can do that in a dynamic way, and the performance of your models is not drastically changed. So this is something that we're going to explore in the future, but just sharing with you at this point. So thank you to all those that support this research. And that's it. If you have any questions.
Thank you, Eliu. I will open up questions. Please, if you have questions, please post them over the chat onto Zoom chat, or please feel free to unmute yourself. While we wait for other questions, let me ask a quick one. So for the training steps, how is the code distributed? Like, how is it that it's easy for someone to take this, take the pipeline and like get it running quickly?
So what we made available was the inference algorithms, right? For the distributed training, we had to work with colleagues at Oak Ridge and NVIDIA scientists as well, because the code that we had available in Summit was not good enough for the problem that we were trying to address. And the reason for that is that many of the big challenges that are used in Summit still require the use of, basic neural nets or image nets. But when you're using experimental data sets, those optimizers perform really, really poorly. So we spent about a month working with them, deploying new optimizers. And this is how this work came to be. If you're really interested in this, we can definitely share that code, but you will have to tweak it for your particular application.
I see. Do we have any other questions? All right.
Quick question from me. So I guess first statement, probably if I'd thought about things, I would have rearranged the schedule such that the DL Hub talk came before Eliu's talk on using DL Hub. So apologies on that. You'll find out more about DL Hub in a couple of talks. I assume there's a lot of dependencies in these types of applications, right? So have you containerized everything? Is that portable across the different backend systems you want to run on?
Yes. So what we have available on DL Hub, you just deploy your PhoneCakes endpoints on a platform, and then you run the analysis. And it is pretty smooth.
Yadu, also I accidentally muted you there trying to admit someone from the waiting room. Sorry.
I suspected that's what happened.
So I said that the software stack that was deployed on DL Hub includes everything to run the analysis smoothly. We tested this on several platforms at NCSA. One is the HAL cluster, but also on a DGX box that they have embedded in that cluster. And the analysis was reproducible. There were no hiccups.